equation. Cosine of theta equals 1 over 3. And here is the relevant graph to look at. There's the curve y equals cosine of x, and y equals 1 over 3. So just by looking at that graph, how many solutions does it look like there are to this equation? Yeah, I thought 4 if you only believe in this picture, or infinity if you notice that it probably goes on forever in both directions. I only have so much space, so I can't draw the whole infinite picture. So it looks like there should be infinitely many solutions. So we would need to find all infinity of them. So, step 1, let's just try to find a solution. So, we want to find all solutions to cosine of theta equals 1 over 3. Let's start by finding all the solutions which lie in a single period. Here I'll suggest between 0 and 2 pi. So let's just try to do that once. Let's find those solutions. I guess here's the graph. The graph of this trig function over one full period. How many solutions are there over that period? 2 of them. Over just the orange bit, there are 2. So let's try to find those 2 solutions first. In fact, let's just find one solution first. What is an angle whose cosine is 1 third? Or what's the name of such an angle? I'm asking for like a formula that gives you a solution to this. Inverse cosine of 1 third? Well, that's the job of inverse cosine. It gives you like the best solution to this equation. So here's one solution. Inverse trigonometry gives you one solution. Cosine inverse of 1 over 3. Remind for me, if you will, what's the range of inverse cosine? So that'll be the solution that lives between 0 and pi. So let's see. There's x equals 0. There's x equals pi. It looks like here is cosine inverse of 1 over 3. And now if you wanted a decimal approximation for that, you could get a decimal approximation. Given that we're walking between 0 and 2 pi instead of 0 and 360 degrees, do you think we're in radian mode or degree mode right now? Radian. Whenever there's not a reason to be in degree mode, we'll be in radian mode. All right, so there's one solution. But there are more, right? Like, there's even another one between 0 and 2 pi that we still want to find. Maybe a useful way to think about what to do next is let's draw like a unit circle picture. So here's a picture of the unit circle. We want to know when cosine is equal to 1 over 3. What feature is cosine equal to on the unit circle? The x-coordinate. So if we want cosine to be 1 third, that means we want x to be 1 third. And the angle we have so far is this angle, cosine inverse of 1 third. How do you get the other angle that has the same cosine? Negative would do, right? Instead of rotating up, you could rotate down by the same amount. I guess we're falling slightly off of the prompt, but this is a valid idea. So here's negative cosine inverse of 1 third. It has the exact same x value. The y value is negative, but I don't care about the y value. We feel pretty good so far? Cool. So, I'm going to put two different things here. Negative cosine inverse of 1/3 is another solution. And I'm going to put two different things in this blank because that doesn't quite follow the written form. I was hoping for you to say 2 pi minus that angle instead of just minus that angle. But right, it gives you the same point on the other side. So I'll draw this purple point. So that purple point, negative inverse cosine of 1/3, where would that show up on this graph? Yeah. Yeah, I'll take the point that I already had, and I just want to make that x value negative. Make that input negative. So there's negative cosine inverse of 1/3. What if you really wanted only the two solutions that live between 0 and 2 pi? That solution we just found, is it between 0 and 2 pi? No. And this isn't part of the font, but sometimes it will be. How would you take that purple point and arrange that it is between 0 and 2 pi? Yeah. Well, let's see. It looks like there's the point I'm looking for. Right, like that's the other solution that happens to live between 0 and 2 pi. It looks like these 2 points differ by exactly 1 period. What's the period of cosine? 2 pi. So if I took that focal point and moved it right by 2 pi, that would get me the point I want. So I guess if I just add 2 pi to that, I would get that other point. So I'll make a judicious use of colors. So inverse cosine of 1/3 is a perfectly fine other solution to use. 2 pi minus cosine inverse of 1/3 is also another solution, and that's the one that's actually between 0 and 2 pi, if you happen to really care about being between 0 and 2 pi. So there's this point, which is 2 pi minus cosine inverse of 1/3. All right. So either using these two solutions or those two solutions, do we now have two solutions that live in a single period of cosine? And in fact, are those all of the solutions that live in that single period? Well, cosine is 2 pi periodic. So now you can get everything that cosine does by adding 2 pi's to stuff. So let's do that. So it looks like all of the solutions to cosine equals 1/3 is given by cosine inverse of 1/3 plus 2 pi k. So that would accomplish taking this point, translating it by 2 pi, translating it by 4 pi, translating it by 6 pi, translating it by 8 pi, and so on. And also going backwards, the k is allowed to be negative. To get the other one, I guess the purple one is the one we started with, so let's use that one. Or negative cosine inverse of 1/3, again, plus 2 pi k. Oh, the 2 pi k's are already written. Does that feel pretty okay? Nice. So there's the strategy to solving a simple trigonometric equation, something that just looks like trig function equals number. Find all the solutions that happen within one period, and then add the period back in. Think we could do that again for sine? Let's do it again for sine. Let's find all of the solutions to sine of theta equal to 1/3. And let's see. Should I start by talking, or should I just be quiet for a bit? Should I continue talking right now? Cool. I will continue talking. So, first things first. Inverse trigonometry will give me a solution. What is one solution to cosine of theta equals 1/3? Nope, sine theta equals 1/3. Yeah. Let's use the inverse sine applied to 1/3. Should I continue saying sine inverse, or should I switch to arc sine? Many people prefer arc sine. No, I'm going to do it anyway.
Get it anyway.
Yeah, it's the same thing. So here is one solution. One solution. Arc sine of 1 over 3. And what's the range of inverse sine? Remind me that? Negative pi over 2 to pi over 2. So that'll be the solution that lives between these 2 points. So I'll be finding like the theta value that's between negative pi over 2 and pi over 2. Well, that's this point, right? That's the solution that this finds. So here's the solution at sine inverse of 1 over 3. All right, well, the next thing to do is find a second solution that lives within a single period of sine. Yeah?
Pi minus inverse sine 1/3.
Yeah, so let's write that down. Second solution, pi minus sine inverse of 1 over 3. And, well, how did you get that? What is the reasoning for that? Where did that come from?
Sine theta is equal to sine pi minus theta.
Yeah, sine theta is the same as the sine of pi minus theta. That sound familiar to people? Alternately, if you like drawing unit circle pictures, let's draw the unit circle picture. There's the unit circle picture. Which feature on the unit circle gives you sine? Y value. So I'll draw this y value at y equals 1 over 3. It might not look like it's drawn to any sort of reasonable scale, but that's okay. So far, we had already found this one. This one is sine inverse of 1 over 3. The other one is the same angle, but reflected over the y-axis. So that would be like, instead of starting at 0 and rotating up, we'll start at pi and rotate up. So instead of theta, we'll do forward by pi, back by theta. So there's like the really quick justification of the identity that you just used. So let's write down that other one. This other angle is pi minus sine inverse of 1 over 3. All right. Now that we've found two solutions within a single interval, let's label them. Pi minus sine inverse of 1 over 3. Now that we've found two solutions inside of a single interval, how do we get all of the solutions? Yeah. Right? We found all of the solutions inside of one interval. Sine will now keep wiggling up and down with the same regularity. Every time it hits this plus a 2 pi, you'll get a 1/3. Every time it hits that plus a 2 pi, you get a 1/3. So let's write those down. So the full set of solutions are sine inverse of 1 over 3 plus 2 pi k, or pi minus sine inverse of 1 over 3 plus 2 pi k. Those ideas seem reasonably sensible? Any questions about those ideas? So, on the next page, we're about to see some flowcharts. If you ever want to solve a trig function, a simple trig function, here's a set of guidance. So let's suppose you want to solve cosine of x equals some constant. Well, first let's imagine what would happen if that constant were like 25. Is cosine ever equal to 25? So what are the solutions to cosine of x equals 25? There are no solutions. The solution does not exist. If the thing you're setting cosine equal to is too big, there are no solutions. If you have the generic case, which is, I guess, -1 less than c less than 1, well, then you can do exactly what we just did. There will be two solutions in a single period. One of them will be inverse cosine. The other one will either be negative inverse cosine or 2 pi minus inverse cosine. take those and add 2 pi k's. There are two weird points in terms of cosine, namely 1 and negative 1. And to see this fact, let's draw a picture. So there's the graph of cosine. So let's look just over a single interval from 0 to 2 pi. So I'll only look from that solid dot to that open dot. How many times is cosine equal to plus 1 in that interval? Just once, because I excluded the other endpoint. So there's only one basic solution to cosine equals 1, namely x equals 0. Oh, and notice negative 0 is still 0, so the second solution would be the same solution again. So the general solution is just 0 plus 2 pi k or 2 pi k. You can do the same thing with negative 1. Over this interval, from 0 to 2 pi, how many times is cosine equal to negative 1? Just once. What's the input that gives you that? What's the x value there? Pi. Oh, so that's the only solution in one full period? So there's only one solution plus 2 pi k. That seem pretty all right? Could we do the exact same thing for sine? Basically, yeah. If you're asked to solve sine is equal to something bigger than 1, then there are no solutions, so you can stop. If you're asked to solve something with negative 1 less than the constant you're setting sine equal to less than 1, well, then you're in good shape. Find the two solutions in a single period. One of them will be inverse sine of c. The other one will be pi minus inverse sine of c. Add 2 pi k's. If you want to set it equal to 1 or negative 1, well, there will only be one basic solution to each, one solution in a single period. Add 2 pi k's to get the full solution. That seem all right? Cool. Tangent's even easier. Let's solve tangent of x equals negative 8 by drawing a picture, and then we'll see that we follow that flowchart exactly. So let's try to solve tangent equal to negative 8. So I'll start by drawing the graph of tangent. You know what, just in order to highlight the difference between the axes and that line, there we are. So by looking at that graph, how many times does tangent cross the line y equals negative 8? Infinitely many. Well, I guess you could count them here and say it looks like 4, but it keeps on going for infinity in each direction. So there are infinitely many solutions. So here's the strategy I'll follow. We'll look at tangent just over one full period. We'll find all the solutions over that one full period. And then we'll add that period back in. What's the period of tangent? Pi. Right. Tangent's different than sine and cosine in that it's pi periodic instead of 2 pi. So let's think about tangent over one full period. There it is over one full period. How many times does tangent cross the green thing over just that period? Just once. Let's find this one point. What's the name of that point? Well, yeah. It has to do with that. It has to do with inverse tangent, though. I want the x value that gives you a y value of negative 8. That means I want, excellent. Inverse tangent of negative 8, which is whatever it is. I guess you could say, well, inverse tangent is odd, so maybe you could rewrite that as negative tangent inverse of 8. But without a calculator, you can't compute that. I don't see an 8 on the unit circle that we filled in, so I don't know what inverse tangent of negative 8 is. Cool. So there's one solution. Is that the only solution that happens in one full period of tangent? Yeah. One full period is just the pink piece. So now I can add the period of tangent back in. What's the period of tangent again? Pi. So here's one solution. If you want all solutions, I'll take, well, you know what, as long as we have that simplification, I may as well use it. Negative tangent inverse of 8 plus pi k. Feel pretty all right? Cool. So let's see that this follows exactly this little flowchart to the right. So, starting solution, so we want to solve tangent of x equals c, we have negative 8. We got a starting solution, x equal to inverse tangent of negative 8. We simplified if possible. It's simplified in a very small way. We have that one starting solution. We added pi k's. Feel all right? So here's the next one that I want you to do, I think. Solve tangent of x equals the square root of 3 using this strategy. And I'll emphasize that you can simplify quite a bit. So what solution are people getting? Yeah. I only caught the end of it. No, just pi over 3 plus pi k. Cool. How many people had as their answer inverse tangent of the square root of 3 plus pi k as their answer? Nice. You're not wrong, but you're also not simplified. So, in order to see that this is a number we know, I'm going to try to convince you that you know the inverse tangent of the square root of 3. So let's draw out the unit circles. So let's see. There's pi over 4. There's root 2 over 2. Root 2 over 2. Pi over 6. Root 3 over 2. 1 over 2. Pi over 3, 1 over 2, root 3 over 2. And let's use this information to compute tangent of each of these angles. So, tangent is y over x. So let's take the easiest one first. So what's the tangent of pi over 4? So there's a thing that tells you. inverse tangent of 1 is pi over 4. Use that way to compute tangent. What does it give you? Compute that y value divided by the x value. So what do you get? Yeah. Yeah. After you simplify, you just get the square root of 3. So, based on that fact, what's the inverse tangent of the square root of 3? And thus that. So, whenever you see a number that you think you might recognize from the unit circle, look at the unit circle and see if it's an angle that you do know. If so, then you don't need to have an inverse tangent in your answer. Just replace it with the thing that you know it is. Seem all right? Cool. Yeah.
So like when we're doing a solution to any of these, but especially tangent, would we have to include the plus pi and k? Like in the solution?
It depends on the prompt. If the prompt says find all of the solutions, then you definitely need the plus pi k. Or, I suppose, if you wanted to, you could write down like 4 solutions in a row and then put some dot, dot, dots as long as the pattern is extremely clear. But then you may as well just put the plus pi k. So then you don't have to explicitly add pi and then 2 pi. Cool. People feel all right? It could be that I'll ask for, like, give me the solution which lives between negative pi over 2 and pi over 2. And then you just want inverse tangent. I might be sneaky, though, and say, like, I want the solution that lives between pi and between 0 and pi. And then, well, you'd have to, like, do some work to get it to be between 0 and pi. You have to figure out which of the general solution does that. In this case, I guess it would be, that's not between 0 and pi, but this one is. So maybe you would want, yeah. So you should include the plus pi k if you want all of the solutions. If you want a particular one, then make sure you're getting the right one.
In order to get total, you just add pi.
Yep. Groovy. Folks feel all right? Oh, yeah. So, we could spend time on this if we wanted to. Yeah, you know what? Fully simplify again. Give me all of the solutions to sine of x equal to negative 1 over 2. And perhaps in the interest of people wanting to see that flowchart still up, I'll flip to the previous page. That's not the previous page. There's a flowchart to follow projected on the screen now. Use that to solve sine of x equals negative 1/2. People feeling ready to come together and talk through it? All right, let's talk through it. Maybe we'll even just start with, give me the answers. What are the solutions to this equation? All right, there are half of the solutions. Yeah, so definitely minus and minus becomes plus. And notice that's a use that's an application of this oddness of inverse sign that's really useful. You can pull out that negative sign so some of them cancel. It simplifies more though.
Does it simplify to negative pi over 6 plus 2 pi?
And what does the other one simplify to?
Pi plus pi over 6.
Pi plus pi over 6. So 7 pi over 6
Yeah.
plus 2 pi k. So notice, again, 1/2 is the number you see on the units formula. So you know what the inverse sign of 1/2 or the inverse sign of negative 1/2 is. Negative pi. That seem like an okay idea? So maybe I'll point this out just because we've seen the oddness used twice. So picture the graph of the following either by drawing them or by just picturing them in your head. Sine, well no, not sine. Inverse sine, inverse cosine, and inverse tangent. And maybe I'll even draw them. Inverse sine. Inverse cosine and inverse tangent. So looking at each of these, tell me, is it even or is it odd or is it neither? That all was.
That's
Okay. Inverse sine, even, odd, or neither? Odd. Which it better be because you use the oddness in this manipulation. I'm skipping over cosine for a reason. Inverse tangent, even or odd or neither? Odd, which is good because we use the oddness in a previous step. Inverse cosine, even or odd or neither? Neither. It doesn't even have the right domain to check if it's even or odd. So you can't do the same positive negative if it's inverse cosine. You can do something different. And I guess pi minus an angle makes cosine negative. So you could say, well, the cosine inverse of negative 1 over 3 is pi minus cosine inverse of 1 over 3. That's not so bad. Cool. All right. So we know how to solve simple trig functions. The strategy to follow is step 1, use inverse trigonometry and periodicity, if needed, to find all of the solutions that there are in one period. Next, you add 2 pi k's or pi k's, depending on what the period is. That seem all right? Well, if I know how to solve something that just looks like sine of x equals a number, surely I can do something more complicated. And that's all that the remaining examples are. We will solve something very mildly more complicated, very mildly more complicated than that, but still not by a whole lot. And we'll keep ratcheting up the complexity each time by 1. So let's try to solve 3 times sine of x plus 2 equals 1. And here's the strategy I'll follow. Step 1, I'll try to just do some algebra to get sine on its own. Because then I'll have it turned into an elementary trig equation, a simple trig equation. And I can use inverse trigonometry. So, tell me, if you start with that equation, then what does that become sine of x is equal to? What happens if you get sine of x on its own? Say that? I hear a -1 thought. I didn't do it, and I didn't check it, so I'm believing you. I'm reasonably confident. You sounded confident. Does that agree? Nice. That is now a simple trig function. Let's get the solutions to that by following the flowchart. So give me one, no, I'm just going to be quiet. Tell me all of the solutions to this equation.
Negative inverse sine of 1/3 2 pi k and pi plus sine inverse sine of 1/3 plus 2 pi k.
That agree with what other people got? That was very fast, so maybe I... So how many people wound up with the negative sign still inside the parentheses in their final answer? Okay, if you had, it wouldn't be wrong, else I would have said you should probably simplify. Especially because pulling the negative sign out meant that a negative sign could cancel with another negative sign. People feel okay? Do people want to see that problem worked out in any more than the 0 detail that I just gave? Okay, people feeling pretty all right. So, this next problem looks super similar. It just involves tangent instead of sine. So I'll take some options here. Either I'll pause and let you do. I'll talk through it if there is demand for me to talk through it, or we will skip it. Is there demand for me to talk through it? Would people like to go through it themselves and then we come together? Okay, cool. Do it, and then we will come together. Cool. So, tell me, what is x? I'll maybe consult with those around you, see if you're getting consistent answers. Negative inverse tangent of 1/5. Cool. There's one solution. How do you get all of them? Plus pi k. Yeah, so that seems like a really simple-minded thing. That's like not a deep idea. But it means that instead of reporting infinitely many solutions, you only reported one of them. So in some measure, you reported like 0% of all of the answers. Cool. Folks feel pretty okay with that? Is there interest in me talking through that one? Groovy. Then, let's carry on. Let's talk through the solutions to something that's more complicated by a degree of 1. And I'll talk through this one because there's an idea that I want to propose, which will, I think, help think through it. So you see that there's just a bunch of signs in there. So the first thing I'll try to do is I'll do the same thing. I'll solve for sine. I'll figure out what sine could be. And so I don't have to write down sine of x so many times. I'm going to make a useful variable name replacement. I'm going to give sine a variable name, maybe s, because that's the first letter in sine. I'm not terribly creative. So let's take s to be sine of x. this equation now becomes 2s squared minus 5s plus 2 equals 0. Does that look like an equation that's easy to solve? Yeah, I guess you could either factor it, complete the square, or do the quadratic formula. What would people be tempted to try? Factor? Complete the square? Quadratic formula? Yeah, okay. A lot of you didn't vote, but I assume that's just because you're doing the thing you're doing instead. Let's use the quadratic formula. Right, the leading coefficient isn't 1, so I think it does factor because I seem to remember rigging this so that it has rational roots. But yeah, let's use the quadratic formula and see what happens. Oh, maybe I'll do something like really weird depending on time to solve this also. Let's try the quadratic formula. So apparently then s should be negative b plus or minus the square root of b squared, 25, minus 4 times a times c all over 2 times a. And carrying on from there, well, maybe it's not even worth like me spending much more time. What do you get when you finish that up at the end of the day? What is s equal to? One half or 2. So this equation splits into 2 equations. Either sine of x is 1/2 or sine of x is 2. We feeling pretty okay? Let's solve both of those equations, and let's do the one that's easiest to deal with first. And then, yeah, time permitting, I'm going to try to do this weird thing. What's the solution to sine of x equals 2? There are no solutions to that equation. What about sine x equals 1/2? And let's read through it. Maybe we'll even start by looking at the unit circle instead of writing down an inverse trigonometry thing. Do you see an angle on the unit circle where sine is equal to 1/2? What angle is it? Pi over 6. So that means that inverse sine of pi over 6 is, no, inverse sine of 1/2 is pi over 6. But that also means that just pi over 6 is one of the 2 solutions. I'll add the 2 pi k. So also, maybe by looking at the unit circle, what's the other angle you see where sine is equal to 1/2? 5 pi over 6? It'll be pi and then back by pi over 6. And then remember to add the 2 pi k. Now, with my 90 seconds left, I don't think that's enough time to make good progress on the next question. Maybe instead I'll try to solve this equation in like a needlessly high-tech way. So that's a degree 2 polynomial. So we have good techniques for degree 2 polynomials. But we also have techniques that just solve polynomials. So let's try to use that. Let's try to use the rational roots test. So by the rational roots test, what's the list of candidates to be a solution to this equation? Well, what's the numerator would have to divide the constant term, so that's 2. So that gives me 1 or 2. Or those same things divided by 2. And then plus or minuses. You could now, if you wanted to, plug in each of these 6 numbers into that and see which one actually solves it. I guess we know in advance it'll be plus 2 and plus 1/2. You could even, what do you get if you replace s with negative s? Well, 2s squared plus 5s plus 2. No sign changes, so the roots can't be negative. So if there is a rational root, it's in that list. Now just plug in those 3 things. Maybe that's easier than using the quadratic formula. Plugging in 1 is something easier. Cool. So I'll stop there. I'm not feeling behind because I have 2 days on the schedule devoted to solving trig equations. What will we do next time? We'll solve that trig equation. if people want to. And then we'll also do other things that ratchet up the difficulty by 1 each time. And that's how we'll spend all of next time. As you're trickling out, remember that the solution, that the review to the exam has been posted. So check out that review. Because I know that a lot of people in the past have struggled with the existence of a course webpage and Canvas. Canvas links to the one on the course webpage also. There should be a link in Canvas to the course webpage for it. And the one in Canvas is the point class. You too. Any things people want to talk about before we get started?